My name is Tino Tereshko. I come from Seattle, which some people have described in the past as the Amsterdam of the United States. Kind of, I guess. So I want to first of all thank everyone for being here and investing time in coming here and listening to us and having conversations with us. Because I heard earlier today that people in Amsterdam have no time. So it's especially important that for us to recognize the investments that you guys have made to come here and spend time with us. So real quick, before we get started, let's take a selfie, especially the people here in the front. On 3, I want you to raise your hands, to smile, to clap, whatever you want. Just make it interesting, okay? And I'll put it on Twitter lately. So let's do it. 1, 2, 3. That's good. That's good. Thank you. So I'm here to talk about analytics and the various spectrums of analytics that are possible today with the advancements in technology by Google and by others. But let's start with a quick little story. You probably have seen these little cars driving around with a 360 camera on top of them that say Google Maps on top of them. For the past 10 years or so, Google has been mapping the entire world, or as much as possible, and externalizing that information through Google Maps, through Google Earth. You're able to take a little yellow stick figure and put it anywhere in the world and walk through the neighborhoods. Right? I do that with neighborhoods that I grew up in that I haven't been there in a while. But the interesting thing is this is, of course, a massive data collection and optimization problem. And it really speaks to how heavily invested in data Google is itself. But the interesting thing here is, up until recently, up until the last 4 or 5 years, this was just imagery, right? You couldn't, and then maybe coordinates and things like that. You couldn't really gain as much insight as possible from this. But with advancements in AI and with advancements in commoditization of computer hardware and improvements in computing power, especially in AI and machine learning, we're able to derive further information from this imagery. So for example, we can understand that the business has turnover, right? There's a new business in place there. So we can go into Google Maps and update the place of business. Or maybe, the sign wasn't there before. Maybe it was a two-way street, and now you can't go this way. So it's very important for us to tell you that you can't go down this road. So all of this, of course, is done automatically through our AI learning capabilities. And so this right here is probably the worst-kept secret in Silicon Valley. Google is very serious about analytics. It says so in our model. It says Google's mission is to organize all the data that's possible in the world and present it for better good for everyone, right? And so Google has built a number of technologies that it uses internally, right, to organize this information. And the premise of Google Cloud Platform is to be able to externalize these technologies and the lessons learned and the power of compute for your benefits. So you can run alongside Google, leveraging the same Google investments in technology and innovation for yourselves as well, which hopefully accelerates your pace of innovation, accelerates your iteration, allows you to deliver faster, better, more interesting features to delight your customers. And the fact that Google has been a data-driven company for such a long time and has built these services that allow you to do some really powerful things with data and analytics has made it fairly easy for us to become a machine learning company as well. This chart probably needs updating, but essentially, for the past 5 or so years, virtually every single product and service that Google has become, in some ways, and often in many ways, AI-driven, right? So if you use Google Photos, for example, right, you can very clearly understand the type of inference that occurs on your content automatically, right? It allows you to create stories based on just the imagery that's happened and the ability to pull out metadata about that imagery. But of course, you can have too much of a good thing, right? Going back to that example where Google has generated a whole lot of photos of a whole lot of streets around the world. And if you need to go back in time and process all that information, that is a very serious computing power. So you can have too much of a good thing, right? You can have too much of a requirement for AI, especially for inference, right? Which is asking the model what the model thinks is happening, right? So in the last few years, Google has been faced with a problem, a serious problem, right? We have too much demand for inference. And we were faced with having to expand into dozens and dozens of new data centers. And if you've ever seen a picture of a data center that Google operates, these are huge things. They're bigger than this venue here. So it's a serious investment, it takes time, it's complex, right? So we implemented tensor processing units, TPUs, and now we're on version 2.0. TPUs are especially optimized for matrix algebra that allows you to essentially infer results of a AI model. Essentially, TPUs allow us to save a whole lot of energy, right? And so these are live inside of Google for the past several years. They're intricate, they're delicate, and they're really important to our infrastructure. So onto a little bit more practical terms. When I talk to data scientists, AI experts, machine learning experts, they tend to say, in day-to-day activities of what they do, some folks tell me, well, I have to operate an H-based cluster because that's where our data is kept. Or I have to take data from, Hadoop, run a Hive query, create a cohort, and feed that into a model that's lives somewhere else. Or I have to run a bunch of SQL queries before I can even feed anything into my model to randomize samples and so on and so forth. So ultimately, folks tell me that 90% of really true AI machine learning workloads involve pure data science or maybe even data engineering, right? So when you're faced with complex problems like that, it's really important to try to minimize complexity, right? Wherever it's not necessary. So this is really something interesting to keep in mind, right? You can get lost in the noise very easily. But then, according to Gartner, a whole lot of projects to try to create, big data infrastructure, data lakes, end up failing. I'm not sure how accurate that statement is, but it's quite possibly true, right? So it's very hard to do big data in 2017, right? Hadoop's complex, HDFS is complex. You need to have a lot of expertise. So how do you compute this? If you want to be an AI-driven organization, and a prerequisite for AI is data science, but 90% of data science projects fail, that's kind of a daunting proposition, right? So I like to use this Django analogy. You guys are probably familiar with Django, right? Especially, it's basically a game where you pile on wooden bricks on top of each other, and you pull out a brick from here and you put it on top. So you want to think about data infrastructure as entirely interdependent. Bricks on top depend on bricks on the bottom, and you want to have a very clean Jenga tower so it doesn't topple. So at the bottom, you can think about this as baseline architecture, right? What I mean by that is you want to have good networking, you want to choose a good public cloud provider or two, you might want to have a really good data center, right? You want to get that right. And on top of that, you want to have really good compute, right? Virtual machines, servers, containers, and good storage, right? Object storage, for example. And that aids you in developing your good applications and databases that power these applications, right? So in order to have good applications, you probably need to have those two right. Only then you can start thinking about a proper data warehouse. You can certainly do a data warehouse without getting all that right, but it really helps you to have the foundational blocks stacked up before data warehouse. But you're probably going to say, Tino, data warehouse is kind of an old term. We don't use that anymore. We have a data lake. Sure. But sometimes data lakes kind of get stale and they turn into data swamps. But you drain the swamp and you have everything right, and now your data lake is so big, you can call it a data ocean now. Fantastic. Well, let's just summarize all that and just use one umbrella: data, large body of water, right? I coined that. You can ask me to use it, but that's mine. Data, large body of water. And once you have data, large body of water set up, then you can start thinking about AI and machine learning. There are some exceptions you guys saw earlier today, and I can talk about them some more, but that's really the lesson here. And of course, it's a Django tower analogy, so if you build a bad Django tower, it's probably going to topple. Hence, the 90% of all data lake projects fail. That's really the lesson here. Okay, so now that I've scared you sufficiently, let's talk about what a modern data analytics stack looks like. There's probably a whole lot of attributes that you can identify that you can say, this is what has to be in a modern data analytics stack. So I have 4 that I want to talk to you about. The first one is separation of storage and compute. And it is a little bit of a loaded term, so let me quantify exactly what's happening here. Separation of storage compute is really a solved problem. It buys you so many options when you're designing your system. If you don't have this, and you are operating at decently sized scale, you should look into this yesterday, right? It's the pros and cons of having this attribute are just tremendous in your favor, right? So this is a solved problem, get it done. Here's what I mean by pure separation of storage and compute. It's exactly that, right? There's a fine line between processing and compute and storage. And that fine line actually represents a very powerful networking, right? Networking that can talk, that allows every node within a data center to talk to every other node within the same data center at 10 gig all at the same time, right? So Google's data centers, last reported, have over a petabit of bisectional bandwidth per second per data center. So that's kind of a requirement. You have to have good networking. But ultimately, in practical terms, you can have your various storage layers, whether you have Bigtable, which is our Google's NoSQL database. You can have Bigquery storage, which is our data warehousing, data lake storage. Or you can have object store, where you keep your cat videos. And you can have Google Cloud Dataflow, for example, which is our batch and stream processing unified programming model and engine. Access all of those, regardless of where they live. Or potentially you can have Bigquery SQL, which is standard, run SQL queries in all of those. Not cat videos, but let's just ignore that for a sec. And you can have your own Hadoop and Spark clusters run on top of that information as well. So I'm not discounting the significance that Hadoop and Spark have in today's environment. It's the momentum behind these projects is phenomenal, right? So we have Google Cloud Dataproc, which is our fully managed Spark, Hadoop, and Flink service. The awesome thing about our service specifically is that you can get clusters very, very quickly, 90 seconds. Hopefully you guys see that over there. 90 seconds is 99th percentile from the moment you push the button to the moment your cluster is live, ready to use. That's very fast, especially within, if you're coming from your own on-premise private data center space, the typical numbers that I hear involve 6 to 9 months, and sometimes even longer. So 90 seconds is just a phenomenal change, right? Enables so many options. And of course, we have pay per minute, right? So you can shut this thing down after 20 minutes if you'd like to, right? You save the results into a storage, that's where the state is. And because we have fully ephemeral preemptible VMs, which kind of disappear every once in a while, in exchange for 80% off of list price. So you can have very quick Hadoop clusters that you can shut down whenever you want, because you pay by the minute, and you actually don't pay a whole lot for it. And so the idea is that Hadoop doesn't really keep a lot of state, unless it's intermediate state. State lives in storage, right? Initial state and output lives in any of these storage pieces. The other really big point here is that data silos are bad, right? You're playing the game of telephone with data, right? When you're moving data around needlessly, ultimately you end up with multiple copies of data. And the funny thing happens, right? When 2 data scientists try to get the same answers to the same problem using the same data, if that data lives in other places, they'll come up with different results. I'm still not sure how that happens. But data silos are bad, and separation of storage and compute allows you not to deal with that. So here's another different analogy that I can use. And first of all, I apologize especially to the CXOs. This is, we don't think of you that poorly from these stick figures. But ultimately, this is what your potential organization could look like, right? Even at a startup, you can have this type of delineation. And you can have your various bits of data living inside of BigQuery, right? From all the way from very, very raw data that comes from application databases and services to data that's potentially sensitive that you don't necessarily want to have floating around everywhere, to real-time dashboards, things that tell you the state of your business. And all the way to data that you can potentially want to externalize from your infrastructure to your third parties, to clients, because they find use in that. So they all have different roles here, right? And the nice thing about our separation as a storage compute, just like with Google Docs or Google Sheets, where you can, in place, share information and share collateral with other folks within your organization as outside, you can do the same thing with our data lake, data body of water services. So IT and ops could potentially have the overreaching role of this organization. They want to own every single data set. They want to administer that. That's fine. And so in our access controls, they say, I'm the owner and everything, right? Just like in Google Docs. But the data engineers may only need to have viewer access to the really raw data sets, the really important data sets, because you don't want to mess that up. But then they're the ones that are creating dashboards. They're the ones that are creating these data sets. And so they have editor access to that. And of course, the obvious follows, right? Your executives get a real-time dashboard in view mode, and you can even share in place without having an FTP server. In place, you can share your data with third parties, right? So they can run SQL analytics in real time without having to do a whole lot of work on top of your data. So it's pretty awesome. And I've said this already. Data silos are bad. It's a relic of old architectures. Try to avoid data silos. So the second aspect of modern analytics I want to talk about is this concept of serverless. And of course, you've heard of the various terms that, or the various contexts within which serverless is mentioned. So the most confined definition of serverless is essentially cloud functions, right? A tiny little piece of code you execute one at a time. But the industry has been extending this buzzword further into identifying some things that have a very, very high level of abstraction, some things that are fully managed, that essentially allow you to use ephemeral, very, very scalable pieces of compute and only pay for the resources that you use. So our serverless analytics kind of central piece here is BigQuery. I was on the BigQuery team before recently, and it's an amazing product. If you haven't used it, you should definitely look into it. BigQuery is our fully managed analytics data warehouse. It does have separation of storage and compute. It has a very, very powerful storage engine that self-optimizes, self-heals. It tries to understand how you're using the storage and burns a whole lot of CPU and RAM to optimize the storage for your workload. It does that on your behalf, so it's opinionated in that regard. And of course, that storage component allows you to share data within your organization or outside of your organization in very elegant ways, right, without having to copy that data around. On the other side, BigQuery has a compute engine, right? It's basically Dremel, and Dremel, you can go read the paper that's published by Google. Dremel executes SQL queries in real time, very, very fast analytical workloads. And BigQuery has an incredibly high level of abstraction. You never have to touch hardware. You never have to define storage or compute, or really not a whole lot of configuration there, and that's on purpose, right? Because we want you to focus on what's important to you. So let's take a look at what BigQuery looks like if you haven't seen it. So this is the BigQuery UI, which is one of the many ways you can interact with BigQuery. And at first, it doesn't really look all that exciting, right? It kind of looks aged a little bit, right? It kind of looks like Gmail from 2004. But just like Gmail from 2004, when you had, what, a gigabyte inbox right away? When you were yelling at your grandma when she sent you a 30 megabyte video because your inbox would explode, and now you get a gigabyte. That's amazing. And so just like Gmail in 2004 hides a whole lot of complexity and a whole lot of power underneath the hood in the simple UI, BigQuery does the exact same thing. So let me show you. So this is, right here, BigQuery Petabyte is a data set, right? Kind of like a database that BigQuery has. And I'm gonna click on this sales partition table here, which is a table that we made up. It's not real data. We did it for the purposes of demonstrating the power of Bigquery. So there's nothing super special about it. I'm going to look at the schema here of this table. What you see here that's really, really interesting. So it's typical, order execution, when it happened, how much. But here we have actually nested structures. Like we have an array inside of the table. It's pretty awesome. So you can have an array of an array, JSON-like structures that are very, very complicated or very simple, but it kind of allows you to have interesting relationships with your data here. So that's the schema. If I'm going to click on what the table looks like, you'll see here that the table size is a little bit over a petabyte. It's a decently sized table. And that looks like a trillion rows. Trillion rows in this table. So the most sensible thing to do with this table is to try and query it live. So I'm going to, I have this saved query here. So I just pushed the big red button that said run query. Oh no, I had the cache turn on. So we're gonna not cheat. We're not gonna have cache. But if you look at this query, the only thing that I'm doing here to really cheat is that this petabyte table has 3 years worth of data. We're only doing, we're only calling a 1 month of partition. But otherwise, it's querying a whole lot of data, and it's got a join, it's got a big old regular expression, it's got a window function, everything you can possibly imagine in a typical query, right? Mixed bag. Oh, looks like we finished this in 16 and a half seconds. So this table didn't have anything special. There's no keys, there's no indexes, we didn't do any optimizations really outside of what the Bigquery service itself provides in terms of automation optimization. All we did was load that data into Bigquery. So that's the demo here. So let's talk about what exactly happened. So I know I've ran this query before, so I know how much resource it takes to execute this query in under 20 seconds. So it's about 3,000 cores. So you could potentially take that data set, and if you have 3,000 cores lying around, you deploy that, assuming you have similar software to Bigquery, you can execute that. You can run your own demo of that if you'd like. And so that's really what we did, right? We rented 3,000 cores from Google for the length of the job. So let's think about this in virtual machine terms, right? Virtual machines take minutes to start. You get per hour billing, maybe per minute maybe. And virtual machines, it's hard to get 3,000 cores very quickly, right? So what Bigquery allows you to do is to go from 0 to 3,000 for only 16 seconds, 20 seconds, and you get the equivalent of only paying for what you consumed. Now the asterisk here is that Bigquery charges not per second, it charges for the amount of data processed, but this is a great proxy to think about when you're trying to relate this to virtual machines, right? But that's all fun and dandy. The really key benefit of serverless is that you get a whole lot of power for very short periods of time, and you don't even care that that's happening, right? All you care about is you have data, you wrote an interesting SQL query, and you push the big red button, and you want to get the results, right? That's what you care about. Like, sometimes you might want to geek out and think about that, but ultimately this is where you live, and that's the benefit of serverless, really, right? So that's a lot of power for very short bits of time. And of course, if you want to extend that to TensorFlow and machine learning technologies, our fully managed cloud machine learning engine service allows you to do the exact same things on top of TPUs and GPUs. So you can rent, ultimately, you can rent lots and lots of resources for short periods of time without having to worry to stand up those resources, manage those resources, in order for you to train your TensorFlow models. And once the model is complete, you can take that into your own environment. You can take that into Google Cloud Platform and deploy it, or even on your mobile devices, for example. And you might have seen this already in other talks, but the one exception to that whole Django analogy that I've used earlier is that there's been a whole lot of research done by Google and by other technologies to train models on large bits of data. And Google has a good amount of data, right? So we've taken our investments in technologies and we're externalized them through simple APIs, REST APIs, right? So any developer can use them, implement them inside of your application. Now you have an AI-driven application, and you can certainly get that next round of funding if you say AI in your name. So the third aspect I want to talk about is real-time. Real-time analytics is also a solved problem. There are certainly use cases where you can have batch nightly analytics hourly, but you have a very easy path to getting analytics on data as it occurs. And this is a very typical path that our organizations take. Spotify has blogged about this quite extensively, and other companies, of course. New York Times is an avid user of this right here. It's a very high level of abstraction across 3 services that allow you to move data from the moment it occurs in your application to the moment that you have pre-computed analytics, right? You have a dashboard that you're trying to develop here. And to the moment that you want to have real-time access to SQL, to your analyst, to data scientists, to his data, all of that is built, right? You just have to implement it. And it's a very popular way of doing things today. The last thing I want to talk about is ETL. I have to do ETL sometimes, and I don't really find that necessarily too enjoyable, right? It's a means to an end. There's no glory in it. So ETL should be easy, right? We should just get data in as quickly as possible, have it as clean as possible, and focus on value again. So I'm going to give you a quick demo what I'm talking about. So I have this data set here called Citibank data. It's just a bunch of rows. I actually took Bigquery's public data sets and I exported them for this demo. So just a bunch of information. And I ran this, I'm gonna run this Bigquery job. It's gonna take this, I need to update my CLI. I need to, basically I'm taking that data and hopefully the internet holds up and I'm going to load it into Bigquery for quick analysis. Wait a minute, got an error. Oh no. No, I'm kidding, I made that. So it looks like the error says at position 751, there's closed double quotes have something inside of them. All right, well, I'm gonna go to, let's go to that line. This is the line that it's talking about. Oh, I see what it is, right. So I have this quotation here, and inside of it is an escape character that Bigquery doesn't like for some reason. And of course, there's an RFC on it that says, for comma delimited values, you can only escape quotes with other quotes. And Bigquery is very pedantic. It likes RFCs, so it rejects your data. So what do we do? Well, we have this other tool called data prep that you can leverage today. And I'm going to create a job instead of data flow that will hopefully recognize that information. So I'm going to go ahead and go through the flow of importing that file inside of data prep. There it is. It's going to load that file in, or at least some part of it, and then it's going to run some statistical analysis to understand what exactly is going on. Right? It's going to try to understand what the data looks like. Did I do that? Yep. It's going to try to understand what the data looks like, if there are outliers, if there are errors, if it's going to try to parse this information, and so on and so forth. So it looks like it created this thing for me here, and this is basically a ETL job, right? I have that file, and it's going to create a job, and this is the recipe that it's going to execute, which is very simple. You can certainly make that more complex. So we're going to look at the data and see exactly what happens here. And now we wait. But the idea here, again, is that wow, it's taking really slow. I did not have enough content prepared to fill this time. But ultimately, what is going to happen is it's going to take that bad row that I throw in there, and it's going to recognize that row. And it's going to say, hey, that is actually an escape character. It's not conforming to an RFC, but we definitely think it's an escape character. So, wow. Live demos don't always work, I guess, so let's forget about that. You're just going to have to take my word for it. So, with a tool like data prep, you have one-click ETL, right? You can take ugly data, as you know, if it works. You can take ugly data that doesn't conform to any standards, and you don't want to write Python code or anything like that. You just want it in one place for you to analyze, right? So data prep is a fantastic tool for that. Under the hood, data prep actually creates Apache Beam pipelines, right? Creates these recipes that turn to Apache Beam pipelines and then executes them on top of Google Cloud Dataflow. So you're familiar with that technology. This is actually a pretty cool way of doing things. So data prep is awesome. So to very quickly summarize, the practice of data architecture, data infrastructure is moving very, very quickly, right? But there are pillars that emerge that become very obvious wins very, very quickly, right? And these pillars can simplify your life, and this is kind of like, can I have things simpler, cheaper, and faster? Yes, right? And this is because the architectures fundamentally change. You can save money and get more, right? That's the lesson here. So that's really the 4 things that I've identified. I'm sure you can find many, many more. I'm going to close this on saying that the whole concept of serverless, the idea here, again, is that we want to provide the highest level of abstraction possible. We want to automate all the noise, all the tinkering, all the things that they're not really that important to you, right? You don't want to tinker. Abstract that away, automate that away, and give you a surface that allows you to create value. Right? So instead of doing very low value and a whole lot of tinkering, we want to flip that equation on its head. So we want to give you the ability to create a lot of value in very little tinkering. That's what serverless means. So thank you very much, but before we finish, I'm going to have Jeffrey and Konstantin come on stage, and we're going to have just a quick little fireside chat where we can take questions from each other and from the audience as well. Jeffrey comes from RTL, and his organization implemented some interesting analytics workloads on top of Google. And Konstantin is from a services partner that helped Jeffrey implement this. Please. Thanks for coming, guys. Jeffrey, can you tell me more about your organization?
RTL, yeah. RTL is not only a TV broadcaster, it's a multimedia company. So we have also a lot of digital assets. Nobody knows, but the RTL Group is the largest content uploader on YouTube in Europe. And we work a lot with the Google products, also in the sales domain. In the analytics domain, and also in the big data domain. Yeah.
So when it comes to big data specifically, it's a big data session. What have you guys done? What did you implement?
We store the data in Google Storage. Konstantin helped us with building we have a Spark platform, so he built the platform based on Dataproc, and we have Bigquery on top of that. So it's a nice distribution of products that we have implemented, and it helps us in all various ways. It's very transparent. It's easy to use the setup. I can go to my business stakeholder and tell him exactly which query takes that much long. It cost me so much euro. If you want to have it faster, no problem. I can put more machines on, and you can have it faster. That's the decision. Up to the business. So that makes it really transparent, but really, really powerful.
So it sounds like your business was, with the help of Google Cloud Platform, was really enabled to perform better analytics and more data. Talk about more?
Yeah, what I like about it is that you bring the decision back to the business. If they want to have it faster, you can have it.
Yeah.
So it's up their decision. If you have it within 15 minutes, I don't mind. We'll make it shorter in 15 minutes. It costs a little bit more, but it's their decision. It's not an IT decision, it's a business decision. That's what I like.
That's fantastic. And so I'm aware that you guys are leveraging Google BigQuery. Can you talk more about this particular piece of our infrastructure?
Yeah, Bigquery helps us a lot in our grow intelligence maturity. So like every company, we have a set of reports that helps you by measuring how many customers you have, how many revenue you have, and blah, blah, blah. But then it happens that customers go away, cancel the subscription, or the revenue drops down. So reports tells you about what's happening. And then you want answers on why people left, why cancel their subscription. Then you have to go into the data. And it helps business people to query large data sets and finding answers on why people left. What was the behavior before they left?
Yeah.
So it empowers, again, business people, not a group of data scientists. They can create, they can do a lot. No, business people, you give access to large data sets and finding answers on the problems you see or arise in your reports. Very powerful.
Yeah. And I wish big data buzzword was actually called holistic data, because it allows you to store very raw information about what's going on with your applications, how your users are interacting with your application, so that further down the line, you can have your analysts understand specifically what the behaviors were, right, and why they left your platform.
Yeah, when you have those answers, then you can ask data scientists to make predictive modeling.
Yeah.
But it's the step in between that you want to have a broader audience in your company. People in the business, marketeers, salespeople, has also access to large data sets.
Yeah.
And it's really important to make that grow to AI and machine learning.
Which leads me to my next question. What's your take on AI and machine learning? What are your plans and what are the opportunities within your organization?
We are a total video company, so we have a lot of content, video content. That's what I like about RTL. So we analyze the content, the video, because it tells me about the quality of the content. So we have a lot of content, but must help me about I want to quantify the quality of the content.
Yeah.
So I use also the video APIs, but we also install TensorFlow and Keras to have a better understanding what's happening on screen, and that generates a lot of metadata, tags, labels, that helps me also in my recommendations, so I can prove that a little bit more. I need to have a better understanding of the quality of content.
Fantastic. So we haven't forgotten about you, Konstantin. So Konstantin was one of the gentlemen that did a whole lot of the heavy lifting on this project. Can you tell us more about what you've done?
Yeah. When I started with the project, they already were using Hadoop and Spark, but they had their own on-prem cluster with a fixed amount of machines. So that was also, for start, it was very expensive because it was always on 24/7, and that meant it was either it was not big enough because they wanted their data now, or it was standing around costing money doing nothing. And it also meant there was one cluster, so if two people at the same time wanted to do something with the data, they had to wait for each other. And there were multiple data scientists, multiple data engineers, and also multiple data analysts. And if one of them is using the cluster, the others are not doing anything useful for RTL. And at the same time, I also noticed that keeping your own Hadoop and Spark cluster up and running can be quite labor intensive. RTL would much rather spend that effort doing useful business things than running after their Hadoop Spark cluster. So I suggested we could move them over to Dataproc and for starters. And then they could stop worrying about maintaining them, and at the same time, like the example showed, if you want a 100-node cluster right now, that's fine. And if your job only takes 10 minutes, then you throw it away. If there's 3 people that want to do something at the same time, you spin up 3 clusters, and then you throw away 3 clusters. You can just keep working. And like Tino said also in his slide, if you separate the data from your compute, 3 people want to work at the same data set, that's also fine. Because you're not tied to that one data set that lives over in that one cluster.
How long did your project take?
The whole project was several months, but it also included mostly understanding the data. One of the nice things about using Google Cloud was that setting up the infrastructure basically took me 15 minutes because I've done it before. But I could just click, I want a cluster. I uploaded their data to Google Cloud, a test set, and one of their existing Spark jobs that they were already running on premise. And within 15 minutes, I had working infrastructure. And I could start spending the rest of the time actually analyzing the data and figuring out what to do with it, rather than babysitting the infrastructure.
Yeah. So going forward, what would be your recommendation if you were going to implement this type of infrastructure in the future?
Well, if you already have a Spark, you can just take your existing Spark jobs that usually work on HDFS and put your data in Google Storage, so you get the data separation. Cloud Dataproc comes with integration for Google Storage, basically the same way you use HDFS. So you can just take put your data in Google Storage, take your existing job, and change the output from HDFS to Google Storage and just run it. Yeah. And that's a great first step.
Yeah. Any other comments either one would like to share about the projects?
No, as Constance, it's easy, relatively easy to manage. So you can allocate your time more on business problems. So the maintenance is relatively easy. It's very transparent. And what I like is that each, as you explained, data scientists come to the office in the morning, they spin up the cluster, and here they go. So they're not interfering with each other.
Yeah.
And they use all the same, the whole cluster, all the applications are there, so they can play around. And today they start this, I want a cluster of 10 machines, and tomorrow I'll do a different type of algorithm, and I'll spin up a cluster of 50 machines. Yeah. Up to them. And I know exactly, as a manager, who is using what. So I can also say, you burn too much, or lower down, or spin up.
Fantastic. Konstantin?
Yeah, that's like Geoffrey said, that really helped like their data scientists. And it also helped later on the project, because the original project used Spark to put their data into an existing, pre-process their data into a normal SQL database. But that means that sometimes that when some of the data engineers are busy, I've literally told them, heard them tell one of the data analysts, like, can you please not do your work until 2 in the afternoon, because I'm busy using the database. And yeah, like, I understand from a technical perspective, because like the data engineer was just keeping the database very busy. But you don't want that. So instead of putting the data into a normal database, we put the data in Bigquery, as you saw. Yeah. And RTL has lots of data, because like Geoffrey said, there's a large multimedia presence on the internet from RTL, not just the RTL label, but multiple labels. And that literally generates billions of data points. And I can just put those into Bigquery. I don't even have to aggregate them anymore. So before, all the data was aggregated, and you could only get the reports that the aggregation was specifically made for. And now all the data is just in there, and yeah, there are some pre-made aggregations to make things easier on the users, but it's basically do whatever you want. And again, because it's serverless, as long as you don't request more compute power than Google has, like you don't make Google crash, then they can go nuts.
Fantastic. And we challenge you to do that. Yes. So we have a few minutes to take questions from the audience, so please raise your hand, and there'll be a microphone coming around. Please, right here.
Thank you. What's the difference between Bigquery and Spanner?
Fantastic question. So Bigquery and Spanner are used extensively internally at Google and by our clients. The easiest way to think about it is Bigquery is great for analytics, whereas things like aggregating lots of information. And Spanner is a fantastic tool to create an application or to have an operational database. Right? And they go hand in hand together. Yeah. And actually both speak the same standard SQL language. Any other questions, please?
I see another question over there.
And over there.
Your 20-second query of what was 3,000 nodes, what's the money being spent?
That's a great question. So that particular query cost about $10 to run. Yep. So Bigquery has two pricing models specifically. One is pay per job, as I did, and for folks who are at a larger scale, who have specific use cases, you can pay a flat monthly fee that includes all your queries. Good question.
Hi. Like a lot of BI departments, in our company, we're a bit of a bottleneck when it comes to data preparation. So data prep looks cool because we could put that out there. How difficult would it be to productionize the output of data prep?
That's a good question. In terms of productionize, you want to put this into a place where analysts can work on it.
Sure, so like an analyst might get 20 files, they do their thing, and then we've got 6,000 files that we need to run through a nightly process, and so that kind of productionizing. Yeah,
that is an intrinsic, that's exactly the use case for data prep, so it's an intrinsic quality of that service.
Actually, we had to do pretty much the exact same thing at RTL. One of the nice things about Bigquery is that next to its native custom drivers that are really fast, it also has an existing ODBC driver. So, and it speaks standard ANSI SQL, so it can talk with anything that can talk SQL over ODBC, and that is basically anything that calls itself a data analytics tool can talk with it. So at RTL, the main tool for business intelligence is business objects, and I just set up an ODBC query, and within a couple of days, business objects could talk to BigQuery, and no one would notice the difference. And there's also several other tools with RTL, just the own departments using their own tools. And as long as they can talk ODBC with standard ANSI SQL, then it just works.
We're essentially out of time, but we'll take one final question right there. Thank you.
Thanks for taking my question. So a lot of analytic projects live in an IT landscape, not just a Google landscape. Can you say something about how to roll out into production both code and infrastructure, and how you see integration with existing, let's say, applications and deployment pipelines? I'm thinking, so how do you use this stuff with Git? How do you roll that stuff?
At RTL, we had our pipelines were in code. There's a tool out there called Airflow. That's also from Apache, and that allows you to model all your data pipelines as code. So there's jobs in there like spin up a cluster, run these Spark jobs, spin down the cluster, and take the output from that Spark job and put it into BigQuery. That's all code. So, and that code lives in a Git repository. So, and there's a Jenkins on top of that Git repository. So if I commit to master, Jenkins runs the tests. If the tests look good, it automatically puts it to the accept environment. And if I hit the button, the same code goes to production.
That's the value of ecosystem that creates orchestration and monitoring, things like that can't be understated, right? So Google specifically invested in partnerships and in supporting open source technologies like Airflow, right? That we've extended into our services. And if there are technologies that are compelling that we don't know about, we want to know about them as well. Yeah. Thank you, folks. I think we've run out of time, but thanks for your time. Great. And thank you as well.